Discuss this theory part of double integration. Okay, so very simple theorem we are going to discuss here. What we have a rectangle S. What will I do? I will write all those things simultaneously. We'll draw the diagram so you can easily understand. What we have a rectangle S. Okay, we have, simply I will mention, we have, what is our S? S is a rectangle. Okay, S is equal to AB cross CD. So we have a rectangle here. I will draw a rectangle. Small diagram I will draw. So this is x-axis. This one is y-axis. Getting here AB, and here we have a CD. So this rectangle we have here. Okay, this is a given rectangle. After that, so this is a result of Riemann integration. So in Riemann integration, you know that, so it's not Riemann integration, but the concept parallel to Riemann integration, since we are discussing double integration. Getting? So what we do, we take a partition of this rectangle. So let P is equal to R1, R2, and so on Rn be partition of rectangle S. Okay, of rectangle S. So that means we are taking a partition of this rectangle like this. Okay, that means this rectangle is further divided into some sub rectangles. So we are calling them as R1, R2, R3, R4. In this way we have. Actually, in 3D, what is happening? You can easily see here. Okay, in dimension, what we are getting, this is x-axis, this is y-axis, and this one is z-axis. So we have this rectangle here. Okay, we have this rectangle here and some surface over this rectangle, some surface over this rectangle. Getting? So it is like this. It is like this. So what we do, we divide this rectangle into some sub rectangles. If you divide rectangle into some sub rectangles, so obviously the volume bounded by the surface and the rectangle is also subdivided into some pillars. Getting now? And the volume bounded by surface and xy plane or that rectangle is nothing but volume of all those spheres. So this is the actual concept. So after taking a partition, what we do, we take, let capital Mi is equal to supremum of f of xy, where xy belongs to Ri. Okay, that means over each rectangle the function will have, this is our function. Getting? The function will have minimum value and maximum value. So whatever the maximum value over each rectangle is nothing but capital Mi. So that means over rectangle R1 function will have maximum value, so that will be M1. Over rectangle R2 function will have maximum value, that will be M2, and so on. Similarly, function will have minimum value also. So infimum of f of xy, so xy belongs to Ri. The function will have minimum value also. See next, okay, this is true for all I running from 1 to n. Next, capital M. Capital M is equal to what? Supremum of f of xy, where xy belongs to R. That means over a complete rectangle, this complete rectangle, the function will have maximum value. That will be capital M. Okay, and that means global maxima, you can say here. And this one was local maxima. Here, this is local minima. Similarly, we can go for global minima. So M is equal to infimum of f of xy, xy belongs to R. So I can give a simple example. If you consider all students of your college, okay, of all students of your college, the students are further divided into some subclasses. That is FY BSc, FY BA, FY BCom, SY BSc. That means it is divided arts, commerce, science, first year, second year, third year, in that way. Okay, so in each class, if you declare the result of examination, getting, in each class you can find the maximum marks and minimum marks. You are getting? So those will be in each class. So those will be capital Mi and small mi. But if you consider all students of all standards and all branches, then also there will be a student having maximum marks. Okay, if you consider all students of a college, and there will be a student having minimum marks. Okay, so those will be capital M and small m. Okay, so such simple concept we have. After that, if you have already studied Riemann integration, you must familiar with next concept, that is UPF. Okay, UPF, that is nothing but summation capital Mi area of Ri, I running from 1 to n. Getting capital Mi ARI. Okay, what it means actually in Riemann integration, we write capital Mi delta xi, that means length into height. So here what we have, we are calculating the volume of pillar, okay, which is formed by because of this partition. So ARI, that means area of this subrectangle, and we are taking the product with height, that maximum value. Okay, so that means area of base into height, that means we are getting a volume of a pillar. Okay, so that is UPF, and we are taking sum of all, so that means you will have UPF. Similarly, we can write LPF also. LPF, can you tell me what will be the definition of LPF? LPF will be summation, here we have to take small mi area of Ri. Okay, so actually space is over here, there is no more space, so I suggest you to make a screenshot of it, and after that we will go further. Please make a screenshot of it. Okay, so the next one is UF. That means infimum of UPF. Okay, infimum of UPF, where P is any partition, okay, of rectangle R. So we have upper sums, right? We have upper sums, but if you change the partition, value of upper sum will be different. So whatever its minimum value, that will be UF. So can you guess what is LF? LF, we take exactly opposite thing. That means here we take infimum, but here we take supremum of LPF, where P is partition of rectangle R. Okay, so after that we can clearly write the relation. Clearly, I can mention clearly. Okay, one example I had given you earlier, that is I'm talking about a simple concept. Suppose if you consider just science, here FY first year, be here second year, and here third year students. Okay, so see, if result of any examination is declared, in each class you can find maximum marks and minimum marks. Suppose in FY maximum marks is M1 and minimum marks is M1. In SY maximum marks is M2 and minimum marks is M2, and here capital M3 and small m3, right? But if you consider all classes, then also there will be some maximum marks and some minimum marks. If you consider all students of all these classes, then also there will be maximum and minimum marks. So can you tell me what will be the relation between them? So obviously, if you consider all students, okay, if you consider all students and if you find the maximum marks, obviously it will be the greatest value. Getting? So clearly I can write capital M will be the largest value and small m will be the smallest value, since we are considering all classes. Getting? So small m will be smallest value. Okay, and capital Mi and small mi will lie between them. Obviously capital Mi is less than or equal to capital N, but it is greater than or equal to small mi. Getting my point? And this is true for each I. Okay, this is true for each I. So equality is also possible. Okay, so I agree, equality is also possible. So that's why I've written this is less than or equal to. This is true for all I. Okay, now I will remove this example. See, and this is true for all I running from 1 to n. After that, what I'm going to do, I'm going to multiply all sides of this inequality by area of Ri. Okay, see, let us do that. M into area of Ri less than or equal to small mi area of Ri less than or equal to capital Mi area of Ri. Okay, and this is less than or equal to capital M area of, just let me write area of Ri, and this is true for all I running from 1 to n, right? So see, as I written here, okay, before a few minutes I have written here small mi into area of Ri. This is nothing but LPF, correct? So this is M into area of Ri less than or equal to, this is LPF, and capital Mi into area of Ri. Okay, just a minute, I need to take summation of both sides, then we can do that. I will take summation of both sides, so let us take summation M area of Ri, I running from 1 to n. This is less than or equal to summation I running from 1 to n small mi area of Ri, less than or equal to summation I running from 1 to n capital Mi area of Ri, and this is less than or equal to summation I running from 1 to n capital M area of Ri. Okay. So after taking summation, see what can we do? See, small m is independent on summation, so that's why it will come outside the summation. So small m summation area of Ri, I running from 1 to n, less than or equal to, see, summation small mi area of Ri, this is nothing but formula of LPF. So this is nothing but LPF, correct? And summation capital Mi area of Ri, this is nothing but UPF. So this is less than or equal to UPF, and this is less than or equal to, see here what will happen, capital M is also independent on summation. See here I is there, so that's why it is not independent on summation, but here M has no any I, so that's why it is independent on summation, it will come outside. Capital M summation area of Ri, I running from 1 to n. See what is happening, area of Ri, that means you know that the rectangle we had subdivided into some sub-rectangles, and area of each rectangle we are calculating, but here we are taking sum of each rectangle. Okay, we are taking sum of area of each rectangle, that means we will have area of entire rectangle. So this is nothing but small m area of complete rectangle R, right? So this is less than or equal to LPF, and this is less than or equal to UPF, and again this is less than or equal to M. This is nothing but same summation area of Ri, that means area of rectangle R. So how to find area of rectangle in second or third standard? We have already studied length into breadth. Okay, so rectangle was AB cross CD, rectangle was AB cross CD, so therefore R, you can write R or you can write S also. Okay, so both you can denote by rectangle. So M, so area of rectangle is B minus A, and here D minus C, less than or equal to LPF. Okay, less than or equal to LPF, and less than or equal to UPF, and again less than or equal to M. So area of rectangle is B minus A into D minus C. Okay, see, therefore I can write M B minus A D minus C less than or equal to LPF. Okay, LPF. But see, what is supremum of LPF? LF. That means LF is greater than or equal to LPF. Getting my point? So LF is supremum, na? It is its supremum. So that will be, it will possibly will have maximum value. This is less than or equal to UF. Okay, and but LF is infimum. LF is UF is infimum of UPF. So that's why UF is less than or equal to UPF, and again we have got here UPF is less than or equal to M B minus A into D minus C. Okay, so my board is over here, so make a screenshot of it, and after that we will go further. Okay, so after that what will I do? I will remove unnecessary terms. So therefore M B minus A D minus C less than or equal to, so this is not required, so I will remove it. So this is less than or equal to, directly I can write LF, which is less than or equal to UF, and UF is less than or equal to UPF, but again it is not required, so I will remove it and I will go for next term, that is M B minus A D minus C. Okay, but see, the very important thing is given that f is integrable. Okay, here I will mention here f is integrable over S, that rectangle S, or you can write R also, doesn't matter. So see, so if function is integrable, then upper integral is same as lower integral is equal to actual integral. So therefore I can write LF is same as UF, and which is same as actual integration, double integration over s. So therefore I can write m b minus a d minus c. This is less than or equal to, both of them are same and having value of integration, and this is less than or equal to m b minus a d minus c. So in this way we proved. Okay, in this way we proved. Simply I will remove this part. So if you make a screenshot of it, you will have a complete proof. Just a minute, let me remove this part. So here we have completed this proof. If you want, you can make a screenshot of it. Thank you. Bye bye.